Osmotic pressure is an important concept in mixtures and solutions. It arises from consideration of a system containing two subsystems separated by a semi-permeable barrier. That is to say, a barrier which can only be crossed by one component of a mixture. There are several examples of such barriers in technology and nature. Ultrafiltration and reverse osmosis membranes used for water purification, or dialysis membranes in polymer science. Cell membranes are examples of semi-permeable barriers that permit the transport of solvent, that is water, but not of solutes. This slide shows at the top red and at the bottom white blood cells, which will be subjected to a cyclic change from isotonic, that is, same concentration of electrolyte outside as inside the cell, to hypertonic, higher electrolyte concentration, back to isotonic, and finally to hypotonic, that is, distilled water. When they're exposed to the hypertonic solution, you'll see the cells shrink and wrinkle up, and when they're exposed to the hypotonic solution, they will burst. Here comes the hypertonic solution. You can see the cell membranes beginning to wrinkle up. Goes back to isotonic solution. Cells go back to their old selves. And now here comes the distilled water. Cells at the top expel all of their hemoglobin and become more or less invisible, and the cells at the bottom, unable to sustain themselves, burst open. So instead of a flexible barrier like a cell membrane, let's consider a simpler system consisting initially of two subsystems, a solution and a pure solvent, separated by a rigid barrier. If we now permit the barrier to act as a membrane that's permeable to only the solvent, how can that system come to equilibrium? At equilibrium, we require the solvent chemical potential to be equal in subsystems 1 and subsystems 2. Problem is, the mole fractions can never be equal. A normal equation for the chemical potential shows this to be true. What's missing from this is that the transport of solvent from the pure liquid into the solution to try to equalize chemical potentials, to try to equalize mole fractions, causes a pressure increase, which we denote by capital Pi, in the solution side in subsystem 1. And this changes the solvent chemical potential in subsystem 1. How much does the chemical potential change due to this pressure? We calculate the rate of change, the gradient of chemical potential with a change in pressure at constant temperature and number of moles. Now, chemical potential is just dg dn, so we can rewrite this as d by dn of the derivative of the Gibbs free energy with respect to pressure at constant temperature and number of moles. That is the volume. So overall we get the rate of change of volume with molecules, and that is simply the volume of a single solvent molecule. Now this pressure difference can be detected, can be seen as a hydrostatic pressure difference between the solution and solvent chambers using a couple of glass tubes, for example, or by an electronic pressure transducer or some other kind of device. This means that the correct equilibrium condition includes that pressure term. So the chemical potential is the standard state chemical potential of the solvent plus kBt times log of the mole fraction plus the molecular volume times the osmotic pressure. That must be equal to the chemical potential of the pure liquid. The pure liquid chemical potentials cancel, and that gives us an expression for the osmotic pressure as minus kBt divided by molecular volume of the solvent times the log of the mole fraction of the solvent. So when the mole fraction of the solvent is less than 1, when it's a solution, pressure difference, delta P, denoted pi here, is established at equilibrium. Notice that the chemical nature of the solute is irrelevant in this example of an ideal solution. Instead of writing it in molecular units, we can write it in molar units, multiplying the top and bottom part of that equation by Avogadro's constant to give the gas constant R in the numerator and the molar volume of the solvent in the denominator. We can also write this in terms of the solute mole fraction x2. x1 plus x2 must add up to 1 for a simple solution, so we can replace the mole fraction of the solvent with 1 minus the mole fraction of the solute. All of these are equally useful and perfectly general expressions for an ideal solution. Let's do an example. What would be the osmotic pressure of a 0.150 mole fraction solution of butylbenzene in orthoxylane? To solve this, we need the molecular or molar volume of the solvent, orthoxylane. This can be obtained from the molecular mass and the density. And we calculate it to be 122 cubic centimetres, that's per mole. Substitute that into our osmotic pressure expression, converting from cubic centimetres to SI units of cubic metres, using the gas constant and normal temperature, 298 Kelvin or 25 degrees C. We calculate the osmotic pressure to be 3.28 times 10 to the 6 pascals. That is 32.3 atmospheres. Osmotic pressures are typically very, very high pressures. The units should cancel out. So the units of the gas constant, joules per Kelvin per mole, multiplied by temperature in Kelvin, and divided by the volume in meters cubed per mole. If we cancel the units out, we're left with joules per cubic metre, which is pascals. In dilute solution, we can take a series expansion of log of 1 minus x2. So dilute solution means x2 is much, much smaller than 1. That can be approximated, as it turns out, to just x2, and then we can further simplify it to molar concentrations by taking the mole fraction and dividing it by the molar volume of the solvent, and that gives us a simplified approximate expression for the osmotic pressure that looks a lot like the ideal gas equation. Osmotic pressure is concentration of solute, molar concentration, times R times T. Now, when using this equation, you have to remember that the osmotic pressure comes from the mole fraction of the solvent in the mixture. This means if you have a solute that dissociates, like sodium chloride, then you have to account for the presence of both the cation and the anion in solution. So you have to include both of them as part of C2, as shown in this expression here. Okay, let's do it. First, what would be the osmotic pressure of a 0.050 molar aqueous solution of sucrose? Using the approximate expression, pi equals concentration times RT, 0.050 molars gets converted into moles per cubic metre, SI units. Gas constant in SI units and temperature 298 gives us 123,879 moles per cubic metre times joules per Kelvin per mole times Kelvin. Once again gives us pascals, and that can be converted into 1.22 atmospheres. One of the common applications of osmotic pressure measurements is to work out the molecular weight of an unknown, very commonly a polymer solution. So for example, if I take a dilute aqueous polymer solution, 0.0423 grams per mil, because I don't know its molecular weight, and measure its osmotic pressure to be 0.032 atmospheres, we can calculate its molecular weight. First, we calculate the molar concentration of the polymer from the osmotic pressure equation. That's 0.032 times 101,325 to give me the osmotic pressure in pascals, divided by 8.314 times 298. That gives me a concentration of 1.31 moles per cubic metre. So the polymer molecular weight is 0.0423 grams per mil divided by 1.31 times 10 to the minus 6 moles per mil, or 32,000 grams per mole. You can do this for low molecular weight solutes as well as high molecular weight solutes like